We're eager
Okay.
to find the story in our data.
Yeah. Good evening, everyone. My name is Rebecca, and I'm with the Allegheny County Conservation District. Thanks for joining us tonight for tonight's webinar, Telling a Story with Your Data with Alarm. This webinar is being recorded, and it will be posted on our website for future views, along with our other recorded webinars from these past few months. We will follow up with a message this week containing a link to the recorded webinar and further resources on these topics. This webinar is part 3 of a 4-part series, Advocating for Your Watershed. And if you haven't already, we hope that you register for the final installment and also spread the word to others. This series is meant to give participants an introductory look into some of the core activities undertaken by Watershed or community groups and volunteers. You can find information on registration links on our Facebook page and ACCD website. Please feel free to type questions into the chat box at any time, and we will address them at the end of the presentations. Without further ado, I'd like to introduce tonight's organization and presenters. About ALARM, or Alliance for Aquatic Resource Monitoring. It's a community science center at Dickinson College that envisions people who are empowered through science to participate in decision-making about their water resources and their local community. Since 1986, ALARM has been engaging communities to use science as a tool to investigate the health of their streams. Julie Vastine directs Dickinson College's ALARM in Carlisle, Pennsylvania, where she enjoys providing technical assistance to watershed communities interested in using science as a tool for change. Julie has worked in the volunteer monitoring and citizen science field for 18 years. In 2019, she was appointed to the National Water Quality Monitoring Council as the volunteer monitoring representative. In 2018, she was elected to the Citizen Science Association. A native of the Chesapeake Bay region, Julie enjoys collaborating with community organizations to build their capacity to monitor, protect, and restore water quality. In addition to her love of working with communities on stream monitoring, Julie enjoys hiking, biking, cooking, and yoga. Suzanne Hartley is the Assistant Director of ALARM, where she provides technical assistance, quality assurance, and data interpretation to watershed groups. Suzanne joined the ALARM team in the beginning of 2020 after completing a master's degree in public science and conservation biology at North Carolina State University. She enjoys exploring and visualizing data to be able to answer questions and tell data stories. Outside of ALARM, Suzanne enjoys gardening, hiking, and cooking. All right, thanks to you both, and I'll pass the share screen baton over to you.
Fantastic. And while Suzanne is pulling up our presentation, we want to give a huge thank you to Rebecca and Amy for inviting us to be a part of your wonderful webinar series. It's always fun to collaborate with you, and so this has been a fantastic process. So thank you again for having us.
Yay!
Yay! And thank you all for spending the hour with us. So as Rebecca said, we're here to give you an experience of how you would tell a story with your data. And with our agenda for our evening with you, Rebecca did a fantastic overview of us. Thank you. We're seeing some replies in the chat introducing yourselves, and so would love to hear from you, your name, location, affiliation, if you haven't put it in the chat already. And then we're going to start diving into this presentation we've got here, building your data story. And we'll start with the scientific process, a quick little overview of water quality standards and their role in this. And then the heart of the presentation is actually going to be looking at some data that Amy provided us for tonight's presentation, and then we'll wrap it on up. So to get started, we wanted to cover a couple of housekeeping items and best practices. I guess in webinar, you don't have the option of turning your camera on, so we'll ignore that. But if you have questions or comments, please put them in the chat. We have some spaces throughout the presentation where we might take a glance at some of those, but the most important thing is we have some questions for you to get you to start looking at the data and giving us some of your own interpretation. And so we really hope that you'll use the chat function. So wiggle your mouse around the bottom of your screen, find that chat, and write to everyone when you have answers to the potential questions we ask. So with that, Shall we, Suzanne? I'm not going to spend too much time on alarm because Rebecca did an incredible introduction. Couple things I just want to highlight. We are based in Carlisle, Pennsylvania. We have a combination of full and part-time staff. And because we have 3 fantastic students on tonight's call, I want to highlight that we also employ Dickinson College students as our Watershed coordinators. And special shout out to Phoebe, Heba, and Olivia. Olivia and Heba helped to make some of the maps that you'll see, and Olivia's been helping with data visualization. So you'll be seeing elements of their work throughout the presentation. And we'll move on ahead. Not going to spend too much time on this, but those of you who know us and have worked with us over the years, looking at you, Wendy, with Creek Connections, and Sue, you've seen this map before. This is the summary of Alarm's community science work over the course of our 34-year history, from acid rain to helping communities design and implement their own water quality monitoring programs, to some standardized monitoring programs as well, some related to fracking and some related to Chesapeake Bay cleanup efforts. So not going to spend too much time here, and we're going to get right into the heart of our presentation. So we're all here to talk about finding the story in our data, and oh, what a fun process this is. When you're setting out to monitor, you're investigating water quality, you're investigating the health of your waterways. And so one of the things we always like to do when we're talking about finding the story in our data is rooting it in those original questions that led you to monitor in the first place. So a lot of you on here, maybe you have monitoring programs. If you do, go ahead and drop that into the chat and let us know where you're monitoring and if you have a monitoring question that you follow. But when you start out monitoring, there's a couple of different things that might inspire you to monitor. You might be interested in baseline water quality health. You might be looking to examine trends, looking at time, seasonal patterns. Maybe you're interested in a specific disturbance within the stream and looking upstream and downstream. Perhaps you're interested in seeing how your stream holds up to the state water quality standards. There's so many motivations for monitoring. But one of the things we always like to promote when we are approached by volunteers or community partners who are interested in monitoring, we always like to start with the study design process. And the study design process is this amazing 10-step tool that brings you through essentially the scientific process and the who, what, where, whys of your monitoring program. And in fact, Olivia, who's on right now, is going to be talking about study design at the Watershed Specialist Conference next Tuesday. So if you're attending, check us out. So we always like to root monitoring within this process and getting back to that original question. Why are you monitoring? How will data help you understand the questions you have about your waterway? How do you intend to use the data? Those 2 questions right there will help inform all the other factors of your monitoring program. And that's all I'm going to say about that right now, but always root it within the scientific process. So one of the things you all have probably seen over the years, and I'm sure it's been touched on with some of the previous webinars and lunch chats that ACCD has facilitated, but really looking at water quality policy and the role of water quality standards in looking at your data story. So it all starts with the Clean Water Act. That was passed many moons ago. We just actually had the 50th anniversary. Maybe we can go to the next slide. The 50th anniversary of the Clean Water Act passing in the Cayuga River. Well, when it burned, but it has periodically burned occasionally since then. But anyway, the Clean Water Act passed in 1972. And really what that did is it helped to set the framework of what the states needed to do to develop standards around water quality. So let's dive into what Pennsylvania has done. And each state has to do their own, they have their own standards to be in accordance with the Clean Water Act. Act. And so there's these regulatory frameworks in place to protect water quality, looking at technology-based controls and water quality controls to ensure that pollution does not degrade a stream or a water body beyond its designated use. So you might be asking yourselves, what is a designated use? And looking at water quality standards. Okay, I thought I knew my next slide and I did not. So anyway, water quality standards get at your criteria, and those get at those key conditions that need to be upheld to maintain those designated uses, which I'll get to. I know, I'm pretty sure in the next slide. So let's go on ahead and go there, Suzanne. So designated uses, every stream segment in all of the 86,000 miles of streams and water edges that we have in our state has a designated use. And that looks at both human and ecological water uses. And so these, once a designated use is identified, then there are specific chemical, physical, biological criteria that have to be upheld with that. So again, it's looking at the optimal use of a stream, and the key determinant in determining whether or not a stream is meeting its designated use or is impaired is macroinvertebrates. We could spend a whole hour talking about water quality standards, but we're not going to do that. But let's go ahead and quickly get through these next slides. So designated uses look at aquatic life, it looks at biological indicators, it looks at recreational uses of the stream, water supply, and things like that. And all of these have specific criteria identified with that. And let's go to the next slide. One of the things to know, as stipulated by the Clean Water Act, the state is required to do a biennial report. It's the integrated report to look at whether or not our streams are meeting their designated use and what is the status. And one of the things that happens is when a stream is not meeting its designated use, it gets listed as impaired. Again, we could spend a lot of time on that, and we're not going to. So let's get right into those standards. So this is my, for the students who have worked in our office, anyone who borrows this has to immediately return to it. It's our coveted copy of the Pennsylvania Code, Chapter 93, which includes all the water quality standards. We have it hyperlinked here as well. And so this really has the key of finding stream segments designated use, and then another key where you look at all the different water quality standards it must uphold. So let's go ahead and move on. But for tonight's purposes, the data that we have from the Allegheny County Conservation District is on Montour Run, and they have a couple of different parameters that they collected data on. So first is looking at conductivity. So a lot of you are seasoned monitors, and so you're familiar with these parameters. Conductivity is the ability of water to pass an electrical current. So the more inorganic ions that you have helps to pass that electricity through the water. And so that's conductivity. pH, oh, we can't be from Pennsylvania and to not talk about pH in our history with acid deposition and acid mine drainage and so on and so forth. A great indication of acidity in water bodies. Temperature, oh, great baseline indicator, wonderful tool to be looking at how landscape is informing water quality. And there's also a little connection in with geology, which we might get to later, might not. Chloride. Now, if anyone's had dinner already, you've put a little sodium chloride on your food, I'm sure. Chloride is a really good parameter to look at too, also related to land uses and human uses of the landscape. Alkalinity is pH's best friend. So alkalinity is the ability of a stream to neutralize or buffer acidic inputs coming into a water body. And then we went on ahead and threw in total dissolved solids. Now, total dissolved solids is not a parameter that was monitored in Montour Run, but since conductivity does not have a state standard, total dissolved solids is a really close cousin to conductivity. We could actually say that they're siblings. So TDS you get with a very specific gravimetric technique and filtering process, conductivity is a great surrogate for total dissolved solids because again, it's getting at those dissolved ions. So I'm going to let y'all take a little gander. We're going to be revisiting these different criteria as we start looking at the data from Montour Run. And with that, I'm going to pass it on over to Suzanne.
Thanks, Julie. And we, hold on one second, and we can't talk about water quality parameters without talking about what influences water quality. And so I'm going to highlight a few things to think about as we start to look at the data of what might be influencing the water quality parameters that we're looking at. So a big one is land use. So land use can impact those water qualities by changing the flow, changing the amount of water going into a stream, which can increase or decrease concentrations of parameters depending on how it's working with the stream. You can have stormwater runoff, bringing all sorts of things into the stream, those chlorides from salts on the roads. You can have other things entering, increasing that conductivity. You can have contaminant pollution, maybe some point sources that are discharging something that has a little high acid or some more chloride, some more salts. And then erosion and sedimentation that can increase that TDS that Julie was just talking about in the previous slide. And then nutrient enrichment, adding the nitrogen and phosphorus to the streams. And so we made thanks to the help of our student watershed coordinators, we were able to create a map of the land use in Allegheny County. So you can see there's definitely a development concentrated there in the center, and then some more forested and agriculture areas around the edges of the county. And then another part of land use is how else the land is being used is for gas and oil extraction. So you can see I think the dark red dots are conventional wells. There's some brighter orange dots to the west of the county that you can see with the unconventional wells, and then some coal mixed in there with the gray squares as well. And then another big contributor to what you see in the water quality. So we talked about the land use, what's above, but also below. The geology also influences the streams. So in particular, you can kind of break geology down into two major categories: carbonate rocks and non-carbonate rocks. So carbonate rocks include limestone, which are higher in calcium and carbonate, and that calcium carbonate adds ions to the streams, as Julie mentioned, so it increases the conductivity. It also allows the streams to be a little bit more protected in the pH, and also adds to that alkalinity. And so when you look at the geology of Allegheny County, you see in the lower half of the county, that light kind of yellow color is the limestone formation. So that's where you're gonna have those maybe streams with higher conductivity and more buffering capacity. And then you have the sand, stone and shale scattered, the shale mostly in the north and a little bit of sandstone scattered in. So then the big goal of finding your story, of being able to tell the story with the data that you have, is being able to take it from that raw data you get from monthly or weekly or however often you're monitoring, and being able to transform it into something that's shareable. It's a story that you can share with others. And so we're going to talk a little bit about how I like to go about that process and how we like to go about that process. Then we started by doing that by first kind of summarizing the data, then being able to find patterns, and then finally telling the story. So I like to break it down into 4 steps. First, looking at the raw data, finding those potential data entry errors and outliers. The second step is kind of taking those raw data and converting it in a way that's a little bit more manageable to start to see some of the trends through averages, minimum, maximum values, ranges. You can do standard deviations as well. And then graphing those depending on your question to start to see what is happening. So looking at how does this change across time, or how does this compare to other sites downstream or upstream. And then finally, interpretation. So now that we know kind of what's happening, kind of trying to figure out that why are we seeing the data that we're seeing? Why are we getting the results that we're getting? And that's probably the 4th step's probably the hardest step, and the one that's sometimes leaves you with more questions than you started with, but that's the beauty of this process, is that it just keeps on going, and you're constantly finding more questions that you want to ask. And so as Julie mentioned, Amy was kind enough to share some data from Montour Run Watershed with us, and so we're going to delve in a little closer to an example for Montour Run. And so the kind of purple outline there is the Montour Run Watershed, and those yellow dots are the sites. So I'm going to dive into a closer look. There was 5 sites that were monitored over a course of 6 months in 2017. 3 of them are on Montour Run themselves, that I named 1, 2, and 3. And then there's also Milk Run and McLaren Run tributaries that are running into Montour Run. So we're gonna, and these were monitored for a variety, most of those parameters that Julie mentioned earlier, not except for TDS, so conductivity, alkalinity, pH, temperature, and a couple others. And so the first step that we did was look at the raw data. And so this can be a little overwhelming at first, but the first step is we looked at the raw data and saw, were there any outliers or potential data entry errors that we wanted to kind of look into a little bit more. And we did find that there were some sites that were monitored in 2018, 6 months later, that we just excluded because we wanted to focus just on what happened in those 6 continuous months that were monitored. So this is something that you can definitely do kind of depending on your question, and see where you want to draw the limits, and if there's any outliers or data that you want to double check on. And then we decided we were going to delve a little bit more into some of the chloride values. And so just want to give a little bit more context for chloride. So chloride is often found in road salts or potentially landfills, wastewater treatment plants, could be discharging salts. It also can come from feed additives or synthetic fertilizers. And normally you'd expect to see concentrations about 1 to 250 parts per million, or other sources say 1 to 100 parts per million. And then the PA standard is around 250 parts per million, or anything above, that's the maximum. It shouldn't be above 250 parts per million. So some of the questions that we wanted to ask with the data are, do chloride concentrations exceed that standard of 250 parts per million? And if so, how often? And are there any upstream, downstream trends that we see in chloride? And it's also a great time if you want to write in the chat, what questions might you have about chloride or any of these parameters or anything at Montour Run. So I'll let you guys take a moment if you have any questions that you're curious about to write them in the chat.
That's a fun thing about data interpretation, is you can constantly be like, ooh, we got this data, but what questions do we have? That's me trying to create some space for people to type in their questions. We're gonna give it another 20 seconds. Suzanne, might as well move on ahead. Oh, is there seasonal fluctuation in concentration? Great question.
That is a great question. Not sure, and not sure one I think we can answer tonight, but one that would be great to ask for sure. So the next step that we did was take that raw data and start to summarize it to see what sites had the lowest concentration of chloride in that 6-month period, and what sites had the highest concentration. And so one of the first things that jumped out to me was that there were 2 sites that their max was above that limit of 250 parts per million, both Milk Run and McLaren Run. So those are the 2 tributaries. And then you can go back then and start to see, okay, so how often did this happen out of the 6 months that were monitored? So we were able to do that and come up with that, out of the 6 months that were monitored, 3 of the sites, you didn't see it exceeding the levels at all. And then out of the 2 tributaries, you see that 4 times out of the 6, so a really high percentage, 67% of the time for those 6 months monitored, Milk Run was above that 250 parts per million, and McLaren, half the time it was above the 250 parts per million. And so then we were able to answer that first question. Do chloride concentrations exceed the standard? Yes, they do exceed the standard. And if so, we were able to answer how often. So the next question we thought we could ask with this data is, are there any upstream, downstream trends in chloride? And so you can map the sites over a course of time, and then it also helps to start to see what are the trends in the site. So you can see Milk Run, which was that one, the site that had 67% of the time is on top there, followed by McLaren. And then you can start to see that the other sites are kind of below. And if you go back to kind of the map, you see that Montour Run is upstream, and then Milk Run comes in, and then there's a site immediately downstream, and then a site down in Montour Run. And you can start to see here, if you can compare them, that as the 2 tributaries that have higher conductivity are coming into Montour Run, the concentration of the Montour Run is slowly going up. So the blue line is the line that's the lightest blue line on the bottom there, is the line that's most upstream, followed by the blue line down the middle blue line. The more brighter blue line is the just downstream of Milk Run, and finally that darker blue line is the one downstream of McLaren. So as these tributaries that have this high chloride are coming into the stream, McLaren Run's concentration is slowly going up. So that you are able to see with the strategic placing of sites, which is awesome, you are starting to be able to see what's happening as those tributaries are adding their concentrations of chloride in. And so you are able to answer the questions. There are some upstream, downstream trends that are starting to happen because of those tributaries that are contributing to the chloride. And if you wanted to, you could do some stats to see how significant that was, but we didn't go that far in, but it is something that you can do to also look at them. And now that's a great question. I think someone already mentioned that they would want to see seasonal concentrations. So that's something that we only had those kind of couple of seasons, and it would require a little bit more time in monitoring and to be able to see those seasonal trends beyond just the warmer months. But is there any other questions that people still have about chloride, remaining chloride, that they would want to have seen, other questions that they would have asked? So I'll give people a chance to write any other questions that may have had. I'm not seeing anything, so I'll move on. Then we also, at this point, we were wondering why are there kind of these chloride concentrations? So we answered the question of, yes, they're higher, and yes, they're upstream, downstream trends, but we didn't necessarily answer the question why. So it looks like there might be some people kind of in the chat kind of starting to hypothesize about why. And so this is where it's really important to pool in those potential influencers. So land use. So here's a little bit more detailed look into land use. And so you can see that there's, you know, more developed areas kind of all over the sites. So that could be contributing to the higher chloride through either runoff. And if you look, there are some gas and oil extraction happening in the in the watershed, particularly around some of the sites. And then for geology, you see that there are, it's mostly we're in the shale, so probably not a whole lot of geology happening there. And yeah, if you guys have any ideas why you think that the chloride might be high, feel free to add them in the chat now.
It is quite a puzzle, isn't it? A mystery of the chloride and elevation. Salt runoff from roads. What were the dates in which these data were collected again, Suzanne?
Yeah, that's a great question. So if you go back up to one of the graphs, you can see that the dates are mostly from May to October. So not really a time period that you would expect there to be ice that salt would be on the roads, but that is often when you do see the spike. So it would be really interesting if it extended beyond into those winter months to see, does it stay this high? Does it go even higher in chloride during those winter months? So getting those like more seasonal patterns, as someone said, you might expect that in the summer months, the chloride would be lower than the winter months.
Yeah, and then another hypothesis was thrown into the chat as well of thinking through a history of, is there a salt industry or something else where it may have gotten into the soil? And, you know, as Suzanne's making her way back into the presentation slide where we were, that's a really wonderful question. And we're looking at these data from Cumberland County. So we don't have that local knowledge. Like we really are taking that look from like 100 to 1,000 foot lens and seeing what we can see using, you know, mapping tools and things like that. And so it really, that hypothesis, Jill, really gets at why local information is really important. Another suggestion was maybe there's a municipal salt dome near the stream. And again, that's where, you know, bringing in perhaps some Google Maps and satellite view imagery could help with taking a look at that. So yeah, we have some question marks around chloride. Yep, and then there is another suggestion, maybe it's fluid from flowback water or something like that. So all great ideas, and we don't necessarily have the answers, and so that might be something to be thinking about as we continue through the analysis. Suzanne, back to you.
Yeah, that's the great part of data analysis interpretation is it usually ends up with more questions. So like, I definitely have that question now of why is the chloride, and it's definitely something that could be further like explored. But moving on, I'm going to move on, shift a little bit now into conductivity to kind of look at, this was another parameter that was looked at. And this one definitely directly relates potentially to the geology of the area, but also those other things as well.
It looks a lot like the chloride map too, I just gotta say.
Yeah, so because chloride acts as an ion, as you see higher chloride, as in the last one, here's the chloride map. If you go back down to that conductivity map, you'll see it's also the same, and it's actually pretty high too. We usually say like 1500 is kind of the kind of measurement that you want, and this is up in kind of right in that kind of line there, being relatively high as well in the conductivity. And then for pH, I don't know if anyone, yeah, I start to see immediately that Milk Run stands out from the other sites. But I also noticed, I don't see the y-axis off to the left starts at 7.6. So all of these are more in the basic site, which if we go back to that geology map for the site, it's not really in a lot of limestone, it's more in shale. So we might not expect to see like the conductivity be that high based on the you not having that limestone contributing as much to those ions. And you also aren't necessarily having that pH buffering capacity because of the limestone. So then Amy was kind enough to share this map with us today, kind of showing where the acid mine drainage is in the region. And so you can see on Milk Run, there's a treatment system that's working just upstream, which might help to explain why the pH stands out a little bit there, and why and in the region as well. So there's definitely treatment going on that might explain some of those elevated pH values that you're seeing.
Yeah, and we just want to just take a little pause and go back to that pH map or graph that you have before that. You know, one of the reasons why we were like, hey, what else is going on in the landscape here? So one of the alarm only monitors one stream. It's in our town, it's Little Tortoise Spring Run, and it is 100% limestone. And so we expect to see these kinds of pHs not quite as high as 8.6, but we see that a lot with purely limestone streams. But for streams that have shale or sandstone underneath of that and don't have that calcium carbonate dissolving and neutralizing the stream from acidic inputs, you can see those stream values of pH getting down to 5 because of acid deposition. And so when we saw that map of very little limestone where these sites were, and we saw this elevated pH, we were like, I wonder if there's a AMD remediation site or two in this watershed. And so that was fun to be able to connect with Amy and get that map that's on the next slide. But just to give you a sense, if it didn't have lime or limestone in it, you would see pHs closer to 5, if not a little less than that, because of our acidic rainfall.
And so it goes hand in hand with that alkalinity is also, with pH is also alkalinity. And so here are the alkalinity values from that site. So you can see that they're also very high. But that if you go back up to the pH, you saw that Milk Run was kind of lower. And then as you might expect with alkalinity, since they go in hand, alkalinity is the ability of a stream to get more acid without having to change its pH value. And you can see that Milk Run had the lowest alkalinity. So following those two parameters are following really closely to each other as expected because they go hand in hand. You see that Milk Run's coming up on the bottom. Yeah, and so this is a great question since we are not from this area. I think I saw someone, Amy, say that there's 5 AMD treatment sites, but do you guys have any other ideas what might be happening in the Montour Run watershed? Any other thoughts about what may be going on to lead to these alkalinity or pH or
Yeah, and there is a suggestion that there's a fair amount of alkaline shales in the area in addition to limestones. What? That's really helpful to know as well.
Yeah, as Julie said before, we got this data, but it always is, like having people on the ground who do the monitoring is seeing things or having that local knowledge always adds all sorts of information that you might not just see from the data itself. So it is pooling in the other pieces of information, whether it be land use, local point source dischargers that start to tell the story. And so that's where it can get complicated without knowing all of those details, what's happening. And then it can lead to more questions to try to find out what are the potential sources or the reasons that you're seeing the data that you're seeing. So this is always the tricky part of interpretation, is finding those missing pieces, figuring out those future questions, like why is the pH so high when you wouldn't expect it because of the type of geology.
Yeah, and there's a couple other hypotheses that keep bringing up unconventional gas drilling and perhaps some of those fluids. In the reports that we looked at the start of the outset of our shale gas monitoring program, you did see that flowback water did tend to have a neutral pH, if not a slightly elevated pH, because sometimes salts can increase pH. And so that is something, but that's, you know, there's not like a standard norm that varies in the geology throughout the entire state. So that could be a potential explainer, but we don't know for sure. So there's a lot of questions here, but I just wanted to address those hypotheses coming into the chat.
Thanks, Julie. So we can kind of review about, this was a relatively small data set, 6 months at 5 sites. But we can see that even with a relatively small data set, there are questions that we are able to answer. So we are able to answer, were the parameters higher than the standards? And so for chloride, yes, there were many months in the 6 months that it was higher than what you might expect or hope. But the other parameters seem to be within the standards. Or for conductivity, we don't quite have a standard for that parameter. And we were also able to see that milk runs, alkalinity, and pH were a little lower than the other sites, but still definitely elevated. But you are able to start to see some trends in how some sites, milk run, there's something different happening to that site than are happening to others. So even with like a small data set, you are able to start to see trends and get some clues and potentially baseline values that you can use in the future if something happens. So I think it highlights the value of all data and small data sets. And at this point, I think we have even more questions. So it kind of it brings back to point, we didn't answer all the questions out there. And so at this point, I know I have questions I still want to ask at the data set, and maybe I think people might have already typed in the chat, but if you haven't put in what questions you still have, either about this stream or if there's a stream that you monitor and you have a question about of your own stream, go ahead and type that in the chat now. What future questions would you have for this stream? Kind of going back to what we've learned, if you were to set up a new study, what kind of questions would you focus on?
Yeah, and that's the beautiful thing about study design is you start out with one question, you collect the data, you do an interpretation, and then more questions come up, or maybe you've answered your questions, and so it can be a cyclical process. We have some community partners that we've been working with for close to 20 years, and we've seen them go through the study design process 2, 3, 4 times. And so that's always like the fun thing about scientific data collection is there's always more to investigate. And while people are thinking about what other questions you might still have about the data, one perspective we haven't brought into this conversation is, you know, to ask Amy, what was the original question that drove the monitoring study? And also, did you answer the question that you were hoping to ask, or that you were asking? So that might be something, if you want to type that into the chat or share, that's up to you. But that's always my question is, did you achieve your monitoring goals here? Ooh, so some ideas that you could add macroinvertebrates into this. Yes, we love us some macroinvertebrates.
That's an excellent, I love that. That would be amazing to see kind of what macroinvertebrates were there, because they tell the story that what's happening maybe longer term than sometimes the chemistry can, because you're catching that snapshot with chemistry, but the biological, they live there. So if something happens, you'll see that they're gone. But macroinvertebrates are an awesome way to study what's happening that you might not capture with the chemical.
We're a big fan of the monitoring trifecta. So when you look at the goals of the Clean Water Act, it's based on chemical, biological, and physical indicators. And so whenever you design a monitoring program, there's always that potential of being able to bring in the different narratives those monitoring buckets can offer. So yeah, fun.
And with that, I'll also just take any questions you have about data interpretation or the data interpretation process, and any questions that might have missed in the chat earlier.
Mm. So there's a question about whether or not we would be willing to put together a webinar dealing with flow measurement methods folks can use. We could do that, but I would actually refer you to the ultimate source on flow, and that would be to get some colleagues in from the United States Geological Survey. One of the things I didn't mention at the outset of our presentation is the funding that we're using to collaborate with Rebecca and Amy is from the Pennsylvania Department of Environmental Protection, and it funds the Consortium for Scientific Assistance to Watersheds. And so that consortia, we are here as a team of service providers to provide free technical and mentoring support to communities interested in monitoring. And so when we have questions like people who are really interested in very specific like flow techniques or monitoring erosion and things like that, that's where having USGS as a partner in Seesaw is amazing. So I would say bring USGS to the table to explore those different flow monitoring techniques.
So yeah, that's a great, we didn't necessarily include the flow data in this particular, but that's definitely a big impactor on potential water quality parameters.
Yeah, I mentioned in the chat that there's some surrogates that you can use when flow isn't one of the original parameters collected. And so again, using USGS stream stats is a good way to get around that, as well as you can use precipitation data as well. And there's some fun modeling programs out there that can help do workarounds based on that. So some of the questions are coming just to the panelists. One of the things, if you're looking to start monitoring, and of course, like we could have spent hours upon an additional hour on a webinar on study design, which we're not doing right now, but one of the processes you go through in the study design process is you look at any and all available data within a particular watershed. And as a result of the biannual reports that PADP puts out, there is a cycle of in-person monitoring that happens on sites around the state, but 86,000 miles is a lot to get to of some waterways. And so there's a lot of modeling that is used, but you might still be able to find historic data collected, and not just by the state, but you might have your county conservation district, you might have academic partners, you might have a watershed group or that had done monitoring before. And so if you are looking to start monitoring, it is good to look at the landscape and talk to your watershed specialist to be like, hey, what do you know about the data that have been collected here? Because then you can build your program off of that. So that's a great question. You definitely want to make sure you see what's available. Yeah, and then another point that Dean is making here is, and we didn't make these maps, was to look at your sources of point dischargers within a watershed. When we are working with community partners, that is often a map that we will make just to get a sense of the lay of the land, is looking at point dischargers and seeing what is going on there. So are there other questions that people have? We covered a lot of ground in a short bit of time.
If I don't see any, I also have some few tools and resources I'd love to share of places to get started for that I think are easy to use to kind of start to get your look at how to interpret data. So we are a part of the Chesapeake Monitoring Cooperative, which does have a data interpretation and synthesis methods manual, which is amazing. So you can check that out on our website, on CMC's website. There's also, as Julie shared earlier, the PADEP integrated report, which shows you those impaired streams and why they're impaired. So you can get a sense if there's a stream that you're monitoring, kind of what's happening at that stream and what you might want to keep an eye out for. There's also, there's a tool by Stroud, which I find pretty amazing, called Model My Watershed, where you can click on a point and it'll delineate the watershed and it'll give you land use stats. So you don't have to make maps like I did, but or that we did, our watershed coordinators, and you can get point dischargers on that map as well as some other terrain and other information there as well. And then there's I did find this like karst density map that shows you the carbonate versus non-carbonate for a quick glance. So these are all quick glance tools to get started, to try to pull those pieces together if you do have data and are starting to try to figure out how to connect those pieces together. So these are some resources that I found easy and simple to use.
Yeah, we'll include all of these links in our follow-up email tomorrow with a recorded webinar and links to Alarm's website too, and anything else comes up. So thank you for including those. Any last questions for our guest speakers? Well, thanks to all of you for attending, and thank you so much, Suzanne and Julie. That was outstanding. We're so grateful. Yeah, so I hope everybody has a great night.
Yeah, and thank you so much, Rebecca and Amy, for organizing this series and having us be a part of it. It's just a wonderful resource that you're putting together, and appreciate being invited to the table. So thank you so much.
Thanks. Well, everybody have a great night.
Bye.
Bye.